I wanted to point out that I uploaded the remaining pieces of the homework 4 answer key last night. I'm still a little unhappy with how clear the logarithmic time scale of error propagation is. I found a paper, which is the Lorentz 69 paper, by digging through Vallis's writing on it and then going back. That seems to be where a lot of the ideas originate, but it's not easily connected to the particular integral that Vallis suggests calculating. So I still think there are quite a few missing pieces. I don't know. A problem that turned into something that was considerably harder than I had imagined it would be. So I guess that's a lesson maybe. So today we're going to discuss the paper by Qing Li, which is linked from the on the web page. And so I guess the main point of it is that it's, oops, I should actually change that. Discussion of paper. So what this paper is it's really it's a comparison of a lot of different vertical mixing schemes in the ocean. So vertical mixing schemes are the the way that a climate model takes account of all of the kind of boundary layer forcing effects that we've been talking about. So we've been talking about the kind of study of the boundary layer, but in order to put boundary layer turbulence into a climate model, you have to boil the whole idea down into something that's pretty simple, just a few closed equations. So I wanted to use this paper as an opportunity to kind of see how that goes, to see how much disagreement there is among those kinds of schemes, and then give some sense of how they're evaluated before they're put into a climate model or, in comparison with one another. And hopefully some themes of how that goes will become clear. Some of you are writing papers that are relatively similar to this, talking about essentially biases in climate models or comparisons between different climate models. And so this is a useful paper to kind of give you a state-of-the-art take on how that looks when you're trying to compare the different parameterizations within a climate model. Are there any questions about that? And so, as normal, feel free to unmute yourself and interrupt and ask, or also to post questions to the chat box. It's a little tricky for me to see the chat box at the same time, but I think I've got the window arranged in a nice way today so I can see it. Okay, so we're talking about the oceanic boundary layer, which is, the one, kind of the vision of this turbulent boundary layer that's in an upper mixed layer in the upper part of the ocean. And so this is important because any transfer of heat or fresh water from rainfall or CO2 or momentum or energy from the atmosphere to the ocean has to go through this boundary layer. And it's a pretty dynamic place on the kind of meter scale, as we can see from this little movie. But if you zoom out over maybe a typical climate model grid, which is about 100 kilometers by 100 kilometers, so about 300 times larger in length scale than this domain, or whatever that is, 300 squared times larger in area, that would be, all these features would be enormously tiny. So just infinitesimally small. So the approach is that we use statistical relationships and things like the Monod-Nabokov scaling to represent all of the bulk effect of all those features, rather than trying to directly represent those features themselves, which are far too small to resolve. So what we're going to talk about today is we're going to cover the basic pieces of what's in the paper, but in order to do that, we need to introduce a little bit more than we have been talking about Langmuir turbulence, since one of the primary directives of the paper is to compare how Langmuir turbulence schemes, that is, turbulence that includes energy extracted from the surface wave field into the vertical mixing scheme, versus the non-Langmuir turbulence schemes, which is kind of the traditional Mononabokov style approach to the upper ocean boundary layer. And there are a lot of open questions here, so there are a lot of remaining pieces, but we just want to get started on that and see where we go. So this is the abstract of the paper. There are a lot of people, including me, on the author list, so I will. And what this represented was a bunch of different groups that have been developing Langmuir schemes, trying to figure out what the state of play was among the different schemes that had been proposed and what remaining questions there were. So 6 recent Langmuir schemes and 5 traditional schemes, and by traditional schemes, that's one that doesn't involve the forcing from surface waves, just the normal wind stress and convection forcing. They're brought together into a single column modeling framework. So that means not a full climate model, but just like a vertical grid that's similar to maybe one grid point in a climate model, but without any horizontal connection between different climate model grid cells. So if these schemes were to be used in a real climate model, we would expect there to be a lot of things like, currents that would move stuff around in the horizontal. So we don't expect these results to be directly comparable to what we get in a climate model, even though I will show some climate model sensitivity studies as well. And so the schemes are tested in scenarios versus large eddy simulations. So simulations like the one I just showed that resolve the turbulence across the globe under realistic forcing. So this JRA55 or JRA Go-Go-Do is a forcing product put out by the Japan Meteorological Agency. And it's basically a weather model that's been recreated for a 55-year hindcast. And so a couple of years from that were extracted to use for forcing these. And using initial conditions from observations. So that's another realistic global forcing data set. And then under realistic conditions as observed at a few dedicated studies with moorings. So the non-Langmuir scheme systematically underpredicts the large eddy simulation vertical mixing, while the Langmuir schemes vary in accuracy. So that's basically the state of play. And we'll see a little bit more detail about that. So one of the important things to keep in mind is, so in the single column modeling framework, we don't actually know what the impact would be in a climate model. That's one issue with this design. A second issue with the design is that there's no truth in most of these simulations except for the ones versus large eddy simulations. That there you know what the turbulent result is doing, so you'd have a direct comparison. Why can't we use observations like the mooring observations to constrain what the single column result is? What's the problem there?
Is that because there's interference from other scales?
Yeah, exactly. So because we neglected the horizontal effects of other things that are going on in the real world, those effects might actually be significant at the particular mooring site. In comparison to large eddy simulations, you can eliminate those forcings. So essentially, goes back to the same concept of the Wingard hit on over and over again, was when can you accept a steady, homogeneous condition to compare to observations? Here, we can take a steady, homogeneous, large eddy simulation and compare it to the single column modeling frameworks, or even a transient one if we are aware of how big the transients are. But what we can't do is we can't compare to real observations because of these potential effects of the horizontal pieces. In the atmosphere, you might be able to estimate how important those horizontal effects were by bringing in other observations. But in the ocean, the moorings are usually fairly isolated, so it's quite hard to do that, even though there are some attempts to do that. As we get into the discussion of the submesoscales and stuff over the next few classes, we'll start to think about that a little bit more. So, if that makes sense to everybody, we're basically focusing on 1D mixing, which is going to have some flavor of similarity to the Mononabokov discussions from Wingard. Okay, so here are the schemes without Langmuir turbulence, and then there's this. Each of these has a Langmuir turbulent partner, and then there's one more that has only a with Langmuir turbulence on, the osmosis scheme. So the K profile parameterization is one, which we'll discuss. The energy-based planetary boundary layer is another one that we'll discuss. And then there's a variety of them that are basically second moment closures. So these are systems where they're trying to solve the second moment equations simultaneously. So at the end, we'll come back to how these are set up. But basically, this one, KPP, builds from a Mononabokov similarity style theory with shape functions and scaling laws for the rates of mixing. The energy-based planetary boundary layer tries to close a budget for the potential and kinetic energies, also involving some shape functions that are kind of based on looking at what other schemes do that are more realistic, or large eddy simulations do. And then the second moment closures is an attempt to close all of the second moment budgets, just neglecting the terms you don't know what to do with, like the triple correlations. Okay, so let's say a little bit more about what Langmuir turbulence is, since that's part of the focus. Oops. So remember, this is what the waves in the open ocean look like. There's not necessarily a whole lot of breaking waves, but there are a lot of waves on a lot of different wavelengths. And so what Langmuir turbulence attempts to do is it attempts to figure out how much these waves affect the turbulent structures underneath them in the boundary layer. One of the characteristic features that's seen are these kind of stripes. This is actually in Narragansett Bay. Oops, I meant to delete these pieces. Let's remove them. And you can see these stripes. These show convergence zones at the surface of the water where foam is collecting. So these long overturning cells are converging at the surface and bringing the foam together. You can also see that in oil spills sometimes, where the oil is brought into these kind of streepy patterns. And we're really interested in whether that additional mixing has anything to do with the observed depth of the mixed layer. So here's a movie of the mixed layer depth globally from observations, which is why it's so noisy. But you can see it's somewhere between, say, 10 meters and 1,000 meters, depending on season. It's deeper in the wintertime, and it kind of bobbles back and forth. This is a particular set of observations due to the de Boyer-Montagu, which will be used as the truth for the some of the comparisons I'll show in a minute. And I'm actually going to skip over this because we've already talked about that. So you might say, how is boundary layer turbulence affected by wave-driven or Langmuir turbulence? And how is the climate system affected by Langmuir turbulence? Are two kind of questions. So the second one we're not going to talk too much about today, except to say that the mixed layer depth changes in response to the inclusion of this extra source of energy from wave-driven turbulence. But I want to give you a hint about how the dynamics of how Langmuir turbulence theory goes. So the key aspect of Langmuir turbulence theory is the Stokes drift of the waves. So the waves themselves are not breaking. and leading to turbulence, but they are, if you average over the waves as they go by, you see that there's a Stokes drift. So the average of the Eulerian velocity, sitting at a point, just measuring the velocity at that point, would actually be 0. Waves don't move don't have a net, surface gravity waves don't have a net Eulerian velocity associated with them. But if you follow a parcel of fluid, it actually gets displaced over time. And the way to think about that, which this movie nicely illustrates, is if you're following a parcel, at the top, the Eulerian velocity is a little bigger than at the bottom of these loops. So as you average over wave after wave after wave, you tend to be displaced a little bit each wave. So the orbital velocity, the oscillating velocity, nearly cancels, but doesn't quite, because the velocity near the surface is bigger than the velocity below. So you get a Lagrangian transport, but not an Eulerian transport. And the difference between them is called the Stokes drift. So if you go through trying to figure out what the effect of the waves is on the turbulence, if there was turbulence present underneath, you kind of go through the same story of what happens in the momentum and energy equations normally, and vorticity equations normally, how you produce turbulence in the first place. So you get advection. This is, a Lagrangian transport of the velocity. So you'd imagine that the Stokes drift would also contribute to that. It'll move the tracers, so it'll move the salinity and temperature. That might have an impact on buoyancy gradients, buoyancy fluxes even, in the turbulent sense. There's also a Coriolis force, because the mass itself is being moved along with this. So on a rotating planet, you'd expect that this Stokes drift affects the Coriolis force as well, because it does represent a displacement of the mass. So there's a Coriolis force, and then there's one more obscure force, which is sometimes called the Stokes vortex force. And Nobu Suzuki, who was a postdoc in my lab, suggested that we instead think of it as a Stokes shear force, and I'm going to explain what that is. But it's a little bit like a Reynolds stress. It's a coupling between the Eulerian and Lagrangian flow in such a way that you keep just the lowest order connection between this Stokes drift and any other flows that happen to be in the currents. And so, with it skipping over an enormous amount of math to get to what the Stokes drift is, it appears as another term in the vertical momentum equation. So it also appears in the horizontal momentum equation, but the vertical momentum equation is the more important one for its impact. So here's the vertical momentum equation written in dimensionless form. So we have the vertical acceleration, the vertical the advection of momentum by the Lagrangian velocity, the vertical advection of the momentum here. We're assuming that the Lagrangian velocity is dominantly horizontal here, which would be the case for typical waves, like the ones we just were looking at. And then we have the part of the equation, the pressure gradient and the buoyancy. This is the part that we normally think about being in the hydrostatic balance. And then we might have a viscosity, which we expect to be pretty small. And then here is this residual, which is that it's like a Reynolds stress term, but it's a coupling between the wave field and this flow field. And sorry, this comma is being used to denote a partial derivative, but take a look at what it says. It says when the Lagrangian velocity in the j direction is oriented in the same direction, so this is like Lagrangian velocity dotted into the Stokes drift, but it's the vertical derivative of the Stokes drift. If the Lagrangian velocity is in the same direction as the Stokes drift, then you're getting a downward force. And so it's kind of confusing thing to think about. But here, Nobu made this nice figure, which is helpful. So if this is the direction of the Stokes drift at the surface, and we imagine it decays as it goes down, and you imagine a Lagrangian velocity moving in the potential Lagrangian velocities moving in the direction of these blue arrows, what you get from this force is the direction of the red arrows. So if the Lagrangian velocity and the Stokes drift are in the same direction, you get a downward force. If they're in the opposite direction, you get an upward force. And if they're perpendicular, you get no force at all from this term. So how do we think about this? This will affect flows at the surface. If they're going in the same direction as the waves, they essentially get it's like they're denser. This term plays the same role of the buoyancy as the buoyancy in this equation. So hydrostatic, non-hydrostatic, whatever, this thing will affect it like, if this is true, if the Lagrangian velocity at the surface and the Stokes drift are in the same direction, you get a downward acceleration from the effect of this term. Or if they're in opposite directions, you get an upward acceleration. So that's basically the idea. And so when we look at these Langmuir turbulence features, this time is now we're looking at oil rather than foam. Here's a little airplane for scale. This is after the Deepwater Horizon spill 10 years ago today, actually. Not this image, but the spill was started 10 years ago today. These convergence zones are where that Stokes shear force is pushing downward and accelerating a surface convergence. So if you imagine, so you can see the wave crests are all like this, they're propagating this way. There must be locally here some Lagrangian velocity that's propagating along these filaments. You put those two together, they're in the same direction. So by this little feature, you'd get an acceleration downward. And so you'd get a downward acceleration, which causes a convergence at the surface, which causes the oil to accumulate where it's being left behind because the oil is buoyant. So if that makes sense, that's the mechanism we're talking about. If you do a large eddy simulation including this effect, click the wrong button again. If you do a large eddy simulation including this effect, you can see, here's the direction of the wave field. You can see, this is colored only where the vertical velocities are large. You can see these Langmuir cells, which are aligned with the wind and wave direction. And I can tell you that there is a local velocity anomaly in the same direction, so that Lagrangian velocity dotted into the Stokes drift is what's leading to these larger vertical velocities being oriented in that direction. But here at this front, you can really see that the fact when the front is organized, this temperature the colors here are temperature, that this is a thermal wind, so a baroclinic front, and you can see that when it's aligned with the wind and wave direction, there's a co-alignment of the Lagrangian velocity, which is going along the front, the Stokes drift, and so there's a big vertical acceleration implied by this. And so that tends to strengthen the convergence into this front. The same is true of these smaller features, but they're just not as pronounced as these are kind of more random. This one is really organized by the temperature gradient as well. So the net effect is when you have a Lagrangian velocity that's maybe located in one place in the same direction as the Stokes drift shear, you get a downward force right on top of the peak of that Lagrangian velocity, which drives a surface convergence like this. That's the basic mechanism of the Langmuir cells. So Mengshi's asked why we only find velocities where they're in the same direction. There are velocities in a random turbulent field would actually be kind of all around in lots of different directions. So, if we had isotropic turbulence to begin with, and then a wave field arrived, what would happen is that this velocity field the Lagrangian velocity would be random with the original configuration of the turbulent flow. what happens is that the waves accelerate the convergence into these features where that velocity happened to be aligned. They will decelerate the downward velocity where that those features happen to be opposing each other, and they will do nothing if those random velocities happen to be perpendicular between the Stokes Drift shear and the Lagrangian velocity. So this is a feedback on the pre-existing turbulence in the surface layer to accelerate the formation of structures that have this alignment. And interestingly, if you just put the Stokes drift on, if you just put the waves on and don't have any pre-existing turbulence, you don't get any turbulence. You just get the waves propagating through. They don't interact with the still fluid on its own. You need some random turbulence, and in particular vorticity in the random turbulence, in order to get the right feedbacks kicking into place. So if the Lagrangian velocity here was 0, or was just aligned with a uniform Stokes drift everywhere, this term would be the same everywhere in space, and then it would just be canceled out by the pressure field. It would be like the hydrostatic pressure. It would just get canceled out. So it's really the anomalies in these terms that come from the covariance of the Stokes forces with the in turbulence already present in the fluid that leads to these phenomena. Yes. So so here, well, maybe it's here. So the oil streak would be here along the fastest moving part because of this overturning circulation that's driven by this term. So this term drives a larger downward acceleration here where the Lagrangian velocity is largest. Here the Lagrangian velocity is smaller. The Stokes drift shear is taken to be uniform everywhere. So you get a bigger downward acceleration here, smaller here, which drives these overturning cells. So this fluid at the surface is not only moving that way, but it's moving inward, converging onto this low pressure right here, and that's where the oil will accumulate. It'll be left behind as the water goes down. The oil is buoyant, so it would accumulate along this line.
Baylor, then would because of the overturning cells, would the velocity vector change a little bit, the surface velocity vector?
Yes, it does somewhat. There is a convergence of momentum into this center structure because of that. So there's both an inward velocity component, but maybe even more importantly, there is a UV contribution, or actually, which is here's the U field, and then there's a V from the overturning, and that's converging even more momentum into this central jet. So the reason why there is an instability associated with this, why is because there's a feedback between the formation of these overturning cells and the concentration of the momentum that then further drives overturning.
Oh, okay.
Does that make sense?
Yeah. Thanks.
Basically, I'm going to skip over this slide, but there are observational checks to see whether this seems to work in the real world, and it sort of does. You can check with these little floating buoys. One of the very complicated things to figure out is what happened when the waves and the wind are misaligned. So imagine if there was like an Ekman layer, so there's a spiraling wind-driven current, and then the waves are going in different directions. So you have to think about all that misalignment. Suffice it to say, we spent a lot of time thinking about how to do that right. Here's this little arrows are all our guesses about different guesses at different times. And we came up with a theory that sort of helps to predict what the important aspect of when the alignment between waves and winds is. Okay, so you take all these features, you put it into a climate model, and what happens? Well, as you might expect, the boundary layer gets deeper. because you've added a new source of mixing, a new source of energy to the boundary layer. This was one very early estimate of how much we might get, it's order about 20 to maybe 10 to 20% deeper in summertime, and maybe a little bit less in wintertime. This was one particular theory. This was the second moment closure. This figure shows the second moment closure based version. We had these other theories based on KPP that included this effect, and so we wanted to see how different those different pieces were. That was the whole motivation behind the Lee et al. Paper. And we saw that in the implementations of at least one of these schemes into different climate models not only showed an improvement at the surface, but because the air-sea fluxes were improved, things like the temperature below the mixed layer was actually also being improved. Chlorofluorocarbon uptake, salinity, all that kind of stuff. So we thought that there might be positive impacts of improving this surface mixing. And I'm going to skip over those. This is showing power spectra of LES with wind only versus Langmuir. And basically the important thing here is that on the small scale end of the power spectra, you're getting pretty isotropic in LES. So even though the large scale features have this alignment, the small scale features are pretty much isotropic turbulence. So the at least not right at the surface, but a little bit below, that's true. And so this makes us think that this is just kind of a different mechanism driving the same kind of isotropic turbulence, which maybe the Kolmogorov or Mononabokov theories would apply to. We just need to figure out how to add this extra source of buoyancy, or a buoyancy-like effect. Okay. And it affects entrainment as well, which I'm not going to talk too much about. Okay, so let's get to what the comparison case of the Lee et al. Paper was. So if you take that JRA 55 forcing and analyze based on Mononabokov scaling or something very similar to it, where 90% of the forcing for mixing comes from convection, or 90% comes from this Stokes shear force, the Stokes, the energy that comes from that scaling that we talked about before, or the energy comes from shear production. You can make this kind of a graphic which shows as a function of, basically this is the turbulent Langmuir number. So on this end it's very windy, on this end it's very wavy. That's a dimensionless measure of waves versus winds, which is like the Stokes drift scaled by the wind friction velocity. And then this is basically, up here you have a lot of cooling, down here you have no cooling, and so the no cooling limit has just the waves and wind effects, and the strong cooling effect could be strongly driven by convection. So this is a map of kind of the phase space of where the energy is coming from. And then these white contours show where the probabilities are at taking a point from the JRA 55 forced simulations where you tend to sit in this space. And so you can see that sometimes you get close to the shear-driven turbulence over here. Sometimes you're over here, largely in the Langmuir. Sometimes you're up here in the convection-driven case. Often you're kind of in this multi-forced regime in the middle. If instead it's a diurnal cycle where the surface forcing is stabilizing, you get a kind of similar pattern, because this is, a diurnal cycle is oscillating between this side and this side. So it's back and forth and back and forth and back and forth. So you could kind of anticipate that it would look like similar. And then these little polka dots that are on there are showing where large eddy simulation studies have been carried out. And the hot pink ones are the ones that we use to compare and test these schemes in this comparison paper. Or you could go to a particular location and run all these different schemes. So on this side are the schemes that don't have the Langmuir effect, and on this side are the schemes that do. And this is showing basically the boundary layer depth as a black line, and the colors here, blue is showing that this particular model is colder at that location. This is a side view, so this is time, this is depth. Here's the average of all of the models. So this, this is the typical model, and then which is just chosen to be one of them randomly. And then these other ones are showing the deviation from that. So in comparison to this KPP CV mix scheme, and here's the crazy forcing. So you can see the diurnal cycles, you can see the variations in winds, you can see the variations in waves. It's lagging a little bit behind the variation in winds. This is a pretty complicated kind of forcing, not a steady one at all, that was observed at this this osmosis site, which is in the North Atlantic, kind of in a place where not much else was going on except the seasons were changing. But you can see that there's pretty substantial disagreement between the models. Some of them are much warmer below and colder above, which means that basically they've dug down into the stratification, making the mix layer entrain more water before this typical profile does. Whereas some of them are, like the KPP VR12 is almost exactly the same. So this one actually includes a Langmuir effect, but it includes only one aspect of the Langmuir mixing. So you can see it doesn't really do much. This one includes both the Langmuir mixing and the entrainment due to Langmuir effects. So it has a greater effect. This one is a totally different scheme, which is built to match hurricane conditions. And so apparently it really likes to entrain a lot of water, which may say that the scaling laws that we're using are not quite accurate as we go to very large wind speeds. And then these are the energy planetary boundary layer ones, which you can see are fairly similar to this KPP one, at least under this forcing. And this is the same thing, but a springtime condition. And so you can see that here, the ones that are entraining hard here are also kind of entraining hard in the springtime. But then there's some funny, intermittency and anomalies that persist in some of them versus the others. It's a very complicated comparison, even at one site. And this is what the effect is if we take the global forcing and try and run all the different schemes. And here we can't do that kind of detailed comparison because it's just too much data. But this is just showing the effect of the boundary layer depth as estimated by all the different schemes. So here's the reference, which is kind of an average of some of them. And then here are the other schemes. You can see that there's a pretty substantial variation in depth between these different schemes. This is January on this side, and this is July. The schemes all tend to agree that the boundary layer in the winter hemisphere should be deeper, but they disagree by precisely how much. So these variations, so in the, this one goes up to 300, if I can read it, 300 meters depth, and the variations are about 10% of that. This one, similarly, and this side. Putting it in a box and whisker is maybe a little easier to see. So these schemes over here are the ones that don't have Langmuir effects, and these schemes are the ones that do. This is the box and whisker of all the non-Langmuir ones, and this is the box and whisker of all the Langmuir ones. And you can see that there's a big uncertainty in how the Langmuir effects tend to drive a lot more variability versus when, and this is the delta, so this is that difference between the boundary layer depth from the standard, which is the average over these 5, versus the any one of them. So basically there's a lot of signal in this these Langmuir schemes, but it's not necessarily making it deeper everywhere. Sometimes it makes it shallower. I guess the one standard deviation, it tends to be deeper, but it's still pretty messy. They're still overlapping, so maybe there's no Langmuir effect. It's kind of hard to tell. A different, maybe more precise comparison is shown over here, which is shown, this is the one scheme that doesn't have the Langmuir effect compared to its partner that's exactly the same scheme just turning on the extra effects of waves. And then you can see that maybe the results are a little more systematic, somewhere in between 1 and 10 meter deepening is what you get on average. And this is the same, just using ratios instead of sums down here below. Sorry, that's just saying in words. And we're getting close to being able to sum up and switch over to what these schemes, how these schemes are based, which we'll close on. This is just showing in a map form how much the percent increase of deepening. So this is like the equivalent of that ratio, but -1. And you can see that so this is the January side, this is the July side, and this is the one of the schemes, including Langmuir versus its partner. It's the same scheme except with the waves turned off. This one is the EPBL scheme with Langmuir versus without. This is the second moment closure without. And you can see it's kind of unnerving how much they disagree. So the EPBL scheme has some Langmuir, but it's only about a 10% effect, whereas the KPP scheme is much higher. Lots of places pushing 30%, and then kind of 20% on average. And even worse, the second moment closure seems to have it in both the winter and summer hemisphere, whereas the KPP scheme seems to prefer the summer hemisphere for the deepening effect, which means that the shallower boundary layers are basically being deepened more by the Langmuir effect. So this is pretty complicated. This is not showing that we really know how to do this yet. And in some sense, these schemes are fairly similar in the way they embed Langmuir. So while it's certainly the case that more waves leads to more deepening, we're still in some level of disagreement about how to do it best. And that's the essence of the disagreement over here between the amount of deepening when you turn on the waves. So, to conclude on this part, and this is the end of the Ching's paper, the inclusion of Langmuir turbulence is justified by observations, large eddy simulations, and reduction of climate model bias. But generally, these schemes make the mixed layer deeper, somewhere between 1 and 10 meters deeper, which affects the air sea fluxes, CFCs, carbon, etc. I didn't talk about this bullet, so we can skip that one. But improvement of the scalings versus large eddy simulations has worked really well to date. But not all of the schemes agree well. So we're trying to figure out how to improve this story. So that's where the state of the art sits. Let me say, so are there any questions on this part before I let people know a little bit more about how these schemes work? Okay, let's take a look then. So the KPP scheme, or the K profile parameterization, came out in an atmospheric version in this Tron and Mart paper, and an ocean version in this Large et al. Paper in the mid-80s. This figure is drawn from a 2018 revisiting of how they work. And basically, it's a Mononabokov scaling-based theory where you make a boundary layer coordinate that's based on the boundary layer depth, and then everything else is based from shape functions that scale with this boundary layer and kind of scaling laws for how fast it goes. How do you get this boundary layer? Well, in the traditional Large et al. Scaling and Tron and Mart, they set a Richardson number, a critical Richardson number, which is about somewhere between 0.2 and 0.3 typically. And it's just like what we talked about in class, essentially, that you might have so this is a bulk Richardson number, so it's a delta between the buoyancy evaluated up here near the surface, the buoyancy at whatever depth you're evaluating. Then there's a what about the velocity difference between the surface and whatever depth you're evaluating? And then you might have some unresolved shear. So this is sort of the climate model. There might be some other scalings. This is a helpful tuning factor, which allows you to get the entrainment a little bit more clearly specified in this model. And so if you set this thing, which is a dimensionless ratio equal to 0.2 to 0.3, you pick some critical value, then you can determine at what depth this H, which is the boundary layer depth, best matches that value. So the Richardson number is small, Richardson number is below, and then as the stratification goes up, somewhere you're going to hit the Richardson number where this crosses the critical threshold, and that's how you choose the boundary layer depth. So this is a little bit like backing out what the Mononabokov depth is from something that's easy to estimate from the model. It's not so it's embedded within this scheme is the idea that there would be a surface layer, which is going like the Mononabokov surface layer, and then there might be a free convective layer, which is, deepening by convective mixing. And so just all those ideas that we had before in the WinGuard are kind of parameterized through the way that you choose how to use this dependence on this depth. And so something you might care about, like the vertical mixing of a tracer, would be parameterized with some diffusivity, and that diffusivity would depend on that boundary layer depth, and then a shape function for the vertical velocity and a shape function for the diffusivity. So it would be something like this. So just kind of like those, just like we saw from the Mononabokov theory, it's sort of a shape function based approach. That's why it's called the K profile parameterization, is because it's a diffusivity profile that is assumed, and then you scale for its parameterization. So the H factor here is dimensional. The velocity is also dimensional. I'll show you how it depends in a second. And that's where you get the profile of K. One of the big things that this scheme does as well is we talked a little bit about this in the WinGuard book, is that there is some, in a free convective layer, there can be transport that doesn't depend on the diffusivity. So there's this extra factor, which I'm not going to talk about where that comes from, but the extra factor allows there to be transport even when there's no resolved gradient in that transported field. And the last thing we need to know to figure out how this scheme works roughly is how we find this W. And like you would expect, the W is a combination of the convective velocity scale from the Mononabokov scaling and the horizontal velocity scale from the shear production scaling of Mononabokov. So this is really built in large part out of the Mononabokov theory. Oops, sorry. That was jumping ahead to the other scheme. But are there questions about how the KPP scheme is kind of built? It's really trying to take the Mononabokov theory and convert it to a useful parameterization. So you're just specifying those shape functions. The EPBL theory also specifies shape functions, but rather than adhering to the kind of critical Richardson number thinking about what sets the boundary layer depth, they are more explicit about solving an energy equation. So a turbulent kinetic energy equation, which might have a diffusive transport, it might have a buoyancy, it might have a shear production, it might have a buoyancy production, it might have a dissipation. So the way this scheme works, they parameterize the shape functions for each of these things. They figure out scaling laws for each of them. And then they assume a simplified balance. So you might have something like this, where this is their scaling for the buoyancy production term. This is their scaling for the shear production term. This is their scaling for, this is their scaling for an entrainment term, and this is their scaling for a buoyancy production term. So they're making a balance of these terms, and that's where they get the depth from. And then they also use these same scalings to inform the rates of transfer of these effects. So it's similar to the KPP scheme in that it assumes sort of profiles, but it's different in that it's an energy-based thing. There are lots of other energy-based schemes as well. Things like the K epsilon scheme, which is K stands for the turbulent kinetic energy itself. Those differ from this scheme in that they retain the time derivatives and don't assume a kind of production dissipation balance that the EPBL scheme does. So that's and there's numerical reasons for that, which we can talk about if people are interested. And so again, you need to assume some kind of shape profiles, and this is just examples of the kinds of shape profiles you might assume under different conditions for the buoyancy production. So under neutral conditions, you might have a kind of triangle like this where it's mixing away the stratification and stratifying the flow above, or you might have a stratification where it's mixing versus the stabilized forcing like this, or you might have destabilizing where you're kind of transferring downward because of the surface forcing, spreading out that cooling all the way down, and then mixing down into down here in the stratification below. So these kind of profiles are the sort of assumptions you have to make to get a scheme like this to work. And then the last scheme that we wanted to talk about was the second moment closure, which is an idea that comes from Meller and Yamada, really. Another kind of early mid-80s concept. And what they propose is that you write down all of those flux equations. So not only the components of the energy, like you would need for a TKE-based scheme, like the EPBL scheme, but you write out each component, potentially in an anisotropic way. And then you write out all of the covariances with all of their different dependencies on each other. And then you write out the temperature second moments with all their dependence on each other. And the only thing you don't do is you don't keep the higher order terms. So the turbulent closure problem would say that each of these would have a triple product in it. Each of these would have a triple product. Each of these would have a triple product. So you neglect those terms, or you parameterize it anyway, and then you try and close the budget by finding a closed set of all of these moment equations. So this one is extremely complicated and very hard to get to decide whether you're doing right or wrong, because there's a lot of arbitrary choices and kind of tuning coefficients. All these capital letters represent different tuning coefficients in these interactions between the different terms. And so it's hard, but at the same time, these are nonlinear equations. Like here's a term that depends on both the mean shear and also the Reynolds stress. To get that term right, you have to solve a nonlinear set of coupled algebraic equations. So it's pretty hard to figure out whether this one is working or not and so when we think about these different distinctions, and when the Langmuir effect gets turned into the KPP light scheme or the EPBL scheme or the second moment closure scheme, they're different formulations or how we understand the different results in this kind of a context. Are there any questions about this? So I have a question for you. I was trying to decide whether we should talk on Wednesday about mesoscale parameterizations, that is for the largest scale eddies, or submesoscale parameterizations. I think we might want to start with the mesoscale parameterizations because they're a little better understood, and then work our way down to the submesoscale, which involves both the boundary layer stuff and the mesoscale stuff. But an alternative would be just to skip the mesoscale parameterizations because they are quite different. Does anybody have a strong opinion?
Wait, sorry, why would we skip the mesoscale? Or what would we do instead?
So the mesoscale stuff isn't really constrained to just the boundary layer. It's kind of it's full. They're full depth considerations. One, and two, the mesoscale is not parameterized at all in the atmosphere. You just resolve the storms in the atmosphere when you run a model. So there is no mesoscale parameterization in atmospheric models. And in kind of the next generation of ocean models, there probably won't be a mesoscale parameterization either. So it's a historical oddity that we have these schemes, but it is sort of intellectually helpful in understanding where the submesoscale schemes came from. So I guess I'm a little torn about how to present this. Ming-Chi is suggesting skipping the mesoscale.
Yeah, personally, I agree with that.
Okay, so while I won't not mention it at all, since we do have to have a little bit of it just to understand what the submesoscale do, we'll focus more on the submesoscale. So Wednesday we'll talk about the submesoscale mixed layer Eddy parameterization, and then Friday we'll talk about a symmetric instability parameterization. So those two pieces will come in on the next two classes. And then next week, we will kind of talk about the whole package and try and get a sense of how this stuff all fits together and where the remaining uncertainties lie. Does that sound good to everybody? All right.
Whether can you,
Oh, yeah.
whether, sorry, can you please repeat? My computer shut down and I couldn't hear the last 1 or 2 minutes.
Okay, so we will not focus much on the mesoscale parameterization concept because those are really large scale eddies which are primarily resolved now in both high resolution ocean models but also in atmospheric models. So rather than spending a whole day talking about those, I will skim very quickly over a few concepts that are helpful, but we won't do more than we have already talked about the small Rossby number, large Richardson number limit as we think about the parameterization development.
Okay, got it.
Does that make sense to everybody? So it'll be there so that we can link to the theory we learned from Vallis, but we're really going to be looking at leaving behind that limit and thinking about how it all works together. Okay, great. Sounds good, people. So I'll post those links to those papers for Wednesday and Friday in just a minute, and then people can take a look at them beforehand. The discussion will be kind of similar to how it was today, where I'm kind of going through some of the concepts, but not going too much into detail with each of the papers. That's how I hope we're going to be able to proceed through this. It's a little bit unfortunate that we have to do this online in an online context because this is normally much better as a discussion format rather than a presentation format. But so please do stop me and ask questions. We have time to stretch these days out if you'd like more clarification. Okay, great. Thanks, everyone.
Thank you. Thank you.